My name is Filip Blagojević. I'm from HGST Research, and I'm going to talk about the priority I/O scheduling in the cloud. This is the outline of my talk today. So I'm going to go through introduction and motivation. Then I'm going to try to explain what the priority-based scheduling is. I'm going to go through some high-level implementation details, what we have done, and finally I'm going to present the performance and conclude the talk. So frequently distributed file systems are shared among multiple applications that often have different latency requirements. And we might end up with multiple applications, some of them being requiring real-time response and some of them being some low-priority batch jobs. And examples would be some sort of database that operates, sends queries on a certain data set, while at the same time we have some sort of background, maybe MapReduce job trying to perform some data analytics on the same data set. And in that case, when they are both operating on the same data set, they're going to compete for the hard drive bandwidth, right? And there is currently no mechanism that allows managing the bandwidth of the hard drive. And frequently what we can end up with is having a high priority real-time application suffer really high latency or maybe even starvation because of that. Because of the event actually that we call misscheduling. And misscheduling is, well, I tried sketching it here in this figure, but basically the file system scheduler allows prioritization, right? And we can set certain I/O requests to be at a high priority. Nevertheless, once when this operating system, file system queue gets dispatched to the hard drive, the device has its own internal scheduling, and it always tries to achieve the highest bandwidth. So it's not aware of any prior scheduling that the file system had done. Therefore, some high priority requests might actually experience starvation. And what do people do nowadays to deal with this kind of issue? Well, many people actually use queue depth of 1, so issue only a single command to the hard drive at a time. And here, on the left-hand side, on the left figure, I'm presenting command completion time percentiles. Basically, what this figure is saying, that for the queue depth of 1, we're going to have a very predictable performance. Okay, and the latency is usually going to be less than 10 milliseconds on the hard drive. As we increase the queue depth, we're going to see some commands, some I/O requests having really unpredictable latency and maybe even starve. Therefore, many people just limit this queue depth to 1 because they want to get predictable latency. Now, what happens if we do this, is we limit the queue depth to 1? Well, it's presented in the right figure. Basically, the total throughput of the drive decreases. And we can see as we increase the queue depth, the IOPS number significantly increase because the device is capable of performing much better scheduling. Therefore, by limiting the queue depth to 1, we get expectable or predictable latency, but almost 50% throughput of what we would get with a queue depth of 32. So what we have done to address this problem is we designed a priority-based scheduler that allows passing over the distributed file system I/O priority commands directly to the device. And our priority-based scheduling, that I will call PBS, is based on the IccNCQ priority commands. I will explain on the next slide what IccNCQ is. So in this way, the drive provides prioritization guarantees. And priority commands within the drive are processed in a separate queue in the FIFO order. In this study, we implemented these policies and integrated them with the Hadoop file system just to see what kind of effect this kind of scheduling would have to at the end user. And these scheduling policies are not limited to Hadoop or any distributed file system. We chose Hadoop because it's been used by many people. We will see that the high priority commands significantly outperform the low priority commands. So we compare our PBS scheduler with the native Linux CFQ scheduler and try to see what's going on. So as I said, IccNCQ is an extension of the native command queuing. ICC stands for isochronous command completion. And basically, two features of IccNCQ are important. IccNCQ allows adding time deadline and priorities to the I/O requests. So there is a new queuing mechanism implemented with IccNCQ that allows either normal priorities or ICC priority, which actually means each command can be assigned a deadline by which it has to be completed, which ranges from 10 milliseconds to 64 seconds, or the command can be sent as a high priority command. In this talk, we focus on high priority commands. Okay, so the priority-based scheduler resides between the distributed file system and the device, and it spans both kernel and the user space. It intercepts the the read requests actually from Hadoop file system in this talk, but it can be any, as I said, distributed file system. And also, just to say, we are focusing here in this study only on read requests because they are mostly latency critical, right? So it's composed of multiple modules. So at the user level, we can see PBS JNI, which is just a JNI model that receives the Hadoop file system read commands, passes them to the PBS CDB module that creates the CDB data structure and passes it down through the extended SGIO interface to the kernel part of the PBS that dispatches the command to the I/O device. Software changes are required basically in the entire software stack, including a distributed file system to make all these things work. So I will describe that as well. Something about the user level PBS. As I said, user level PBS communicates to the kernel level through extended SGIO interface. And we bypass, we don't use the standard file system interface, and therefore the information that we receive from a distributed file system, such as file descriptor and offset in a file and so on, needs to be translated to an LBA address and sent below to the kernel level modules. So for that, we do all that at basically user level module through an FIE map system call. Another thing about the PBS scheduler is that, again, as I said, we are using SGI interface and bypass the standard read commands. Therefore, we do not use all the benefits of the standard file system cache. Basically, we don't use the page cache. And therefore, to determine if any data that we are trying to fetch is already in the DRAM, we use the min-core syscall. And if we find that the parts of the file that we are trying to read are in the DRAM, we reroute these requests through the standard read calls. Okay? And as I said, we bypass the page cache and we don't cache the data currently with PBS. But this is only the implementation issue. There is no real reason not to cache the data. So we will do that in the future, but just important thing to know for now is that we only hurt PBS by doing this. And when we compare it to the Linux current implementation in the future, if we improve and add the page cache, then the performance will only increase of PBS, right? So this is something about the kernel level implementation, kernel level module of PBS. Basically, we create the CDB data structure, and that's still done at the user level. And then byte 5, bit 7 actually passes the priority information. This is further passed to the kernel through SGIO and transferred to a task file data structure that further gets transferred to FIS data structure and dispatched to the device. And in the FIS data structure, so all the time we maintain, we keep this priority information. It ends up being in the byte 13 of the FIS data structure. Once the drive reaches, once the command reaches a drive, the IccNCQ firmware actually extracts the information and accordingly schedules the command. We are focused currently only on the SATA commands. And we made this open source. You can download it. So basically, the kernel and the user library, if anyone wants to play with it and see how it works. So these are some software changes, software stack changes. As I said before, we require changing the parts of the, well, almost the entire software stack in order to pass the commands all the way from the distributed file system. And basically what we are testing in this study, we run Hadoop file system and then H-based database on top of it, and then we run a Yahoo Cloud Service benchmark on top of it to and let it compete with some sort of background MapReduce jobs. And we consider this YCSB benchmark to be kind of an example of a real-time data accesses, while MapReduce jobs is something that kind of runs in the background. So in the current implementation of the Hadoop file system, we pass the priorities either through the extended read call or through environment variables. Okay. And now the application that runs on top of Hadoop can either use extended read call or pass the priorities through environment variables. Now this is done in the DFS input string class, but we worked with the Hadoop version of 0.22, so all this might be a little bit different in the latest implementation of Hadoop file system, but basically just following these high-level rules, it wouldn't be hard to re-implement. But basically from the DFS input stream, we pass the priority to the block reader that now operates on the extended communication protocol and passes, so that communication protocol accepts the priorities, passes them to the data node. On the data node side, we also extended the receiver class that passes the priorities further to the block sender. And now the block sender, depending on the priority, can either reroute the request to the PBS or to a standard Linux file system interface. So now, in the H-base, we also had to change the H-base database in order to allow passing the priorities. And basically, H-base runs on top of Hadoop file system. And here we allow priorities also to be passed through an environment variable. So now we end up with something like this, the software stack, basically, where we have an application running on top of it, something, in our case, YCSB, that passes the priorities to the H-base client through environment variable, that further passes the priorities to the H-base region server through extended RPC interface. And now the H-base region server uses extended read calls that we previously implemented in Hadoop file system to pass the priorities to the distributed file system. Now everything goes to the file system, and eventually the Hadoop file system data node decides if the command is going to go through PBS or standard Linux interface. Okay, so this is something about the experimental setup. So as I said before, we run YCSB, which is Yahoo Cloud Service Benchmark, basically performs random reads on the H-base database. So runs on top of H-base, that runs on top of Hadoop file system, and we let it compete with the MapReduce applications. And so we run YCSB once with high priority commands through PBS, and let it compete with the MapReduce applications. And the second time we run YCSB with low priorities, well, basically rerouting all IOs through Linux scheduler and let it compete with MapReduce applications. Okay, and this is our hardware setup that we use. Basically, 4 nodes, each of them 24 gigabytes of DRAM, 4 hard drives per node. Node 0 is reserved to be a metadata server for Hadoop file system, and the rest three of them are used as data nodes for storing data. So the local file system we run on the nodes is ext4 with the CFQ scheduler. And we cache all Hadoop metadata in the DRAM. And basically, I'm talking here about the metadata that is associated with the Hadoop block that is default size of 64 megabytes. So each of these Hadoop blocks, Hadoop file system blocks actually, has a small file associated with itself that contains certain information such as checksum, right? And we checked in this graph all the way there, EXC family of the file system, local file systems, tend to store large data at the beginning of the LBA space, while the small files get stored at the end of the LBA space. Now, when we just use Hadoop initially to put the data in it, we get something like this. All the block files are stored at the beginning of the LBA space, so at the OD of the hard drive, while the metadata is all the way at the end. So basically, now accessing this data requires multiple HDD accesses, right? And this is maybe a known thing. I think I saw it somewhere, Hadoop people talking about it. But just to avoid, it is something that is implementation dependent, maybe can be fixed, but requires a lot of Hadoop changes. So we just cache all the metadata and limit the drive accesses to a single access, basically. Okay, so these are the performance. Basically, as I said, the MapReduce jobs we use to let YCSB compete with are the word count that is running on the 50 gigabyte large data set and the row counter that runs on age-based data, basically. So it counts the row of the age-based database. Up to 4 map and reduce tasks per hard drive, which means up to 32 jobs per node. But I mean, they don't always run at the same time, right? Because there's a dependency among the tasks. So here in the left figure, y-axis represents the number of YCSB threads that we run. And if you look at the bars, they represent the average latency for YCSB commands when we run it with high priority through PBS, and that is the blue bars, and when we run it with low priority through Linux scheduler. So on average, we can see that PBS significantly outperforms Linux, and this difference increases as we increase the number of threads. Then also there is a blue and the yellow line, which represent 95 percentile latency. Again, we can see that PBS is much better. So the lines are associated with the right-hand white axis, right? Very similar results we get even with the other application row counter when we run YCSB with row counter. This is a conclusion. So basically what I was trying to say, yes, we have this misscheduling that occurs because lack of the communication between the file system and the device, right? And there is these new commands, new SATA commands that we try to use to actually implement some sort of communication and pass the priorities. And the initial thoughts were just to see how this will affect the end user and if it will at all. And it turns out that in certain situations it's much better than just having normal default scheduling. Now, there are many open questions, right? So, of course, having a large number of priority commands will perform starvation of the low priority commands, right? So maybe there is something we want to do about that. Maybe we want to use the IccNCQ deadline commands, or even try to do some host sites deadline scheduling to well, not deadline scheduling, but basically increase the priorities of the starving commands, right? Then that's probably part of the future work. Then also multi-level priorities. Not sure if that would be interesting and if people would actually use it. Finally, yeah, what I described here, we have all these commands that are kind of pre-assigned. We have applications that we define to be high priority or low priority. The question is, can we do anything about doing some sort of automatic priority assignment to different I/O requests? And again, I would like to acknowledge actually two of my colleagues that are not anymore working with us, Marcos Anvidio and Jana Koshia, but they have been the initial implementers of the kernel module. And thank you if you have any questions.
Very good work. I have a question. In 2011, in the SOSP, there's also a work on the priority IOs. So can you comment what's the difference of the...
I think they didn't pass actually the priorities to the drive, as far as I know. They have been using different schemes to throttle the commands and to tweak the file system scheduler to allow some predictable latency. But as far as I'm aware, they have not been able to pass the priorities to the device.
You mean the device controller for the storage?
No, to the actual device, to the hard drive. Because the hard drive is essentially the one who has to know about the priorities, because otherwise the hard drive will reorder the commands in order to achieve the highest throughput, or whatever the algorithm hard drive is using, right? The elevator algorithm or whatever, right? If it doesn't have any information from the host, what command should be processed and should not be starred, then the hard drive cannot do anything about it.
Okay, thank you.
Mm-hmm.
Vasily Tarasov, Stony Brook University. I think it's a great work.
Thank you.
I encountered this problem multiple times. So the question that I have, also related to the related work. In transactional storage in 2010, there was a work that was limiting and dynamically changing the depth of a queue.
Oh, that is from Seoul, right? Korea, I believe you're talking about.
So my question, I understand your approach is completely different. Do you have any numbers that compare your approach to their approach?
We didn't directly compare, we didn't take the numbers that they have and directly compare it to what we have. Just didn't do it. There is no reason not to do it. But again, I believe they have done only the user level thing. And actually, in their work, I believe they say that what they do is kind of a step towards getting better scheduling, but nothing can be done unless you really consult the device. So I think this is the right way to go. We have to have some integration with the device, but no, going back to your question, I didn't compare the results to what they actually got. Yeah. I mean, we can talk about that later, and if you're really interested, it wouldn't be hard to do something like that.
Do we have time for a second question? Yeah. So, and I noticed that in your benchmark, you were using quite small I/O sizes, 10 kilobytes, if I'm not mistaken, right?
For YCSB, yes.
Yeah, right. So did you run any experiments with larger I/O sizes? Because in these cases, already passing all of the requests to the device, to the controller, matters much less, right?
Right. No, and you're totally right. And I was trying to avoid that. I think what I was trying to focus is exactly the fine granularity requests, because I think they are the most likely to get hurt by the unfairness of the scheduling. And if we are going to have latency critical applications, I believe they're going to use fine granularity requests. And you're right. So having large requests, probably all this would have less impact on larger granularity requests. Yeah.
So the reason why I'm asking this question, because very often the upper layers will try to aggregate the request and read bulk of the data and read ahead and such kind of things. So I'm not sure how reasonable, how realistic it is to assume that the request will be small size.
In a way, I mean, what you're saying is correct, but that's why, looking in a cloud environment, you're really likely to have large number of users or large number of edge-based users. They're going to all have their own queries, like thinking of a Google-like system or Facebook, where everybody wants to get their own data quickly, right? And in that case, you're going to have a lot of users trying to access small granularity of different pieces of data, such as photos or things like that. And I think that is the area where this work would fit the best. But you're right. I mean, it is also possible that some requests would be aggregated. And
thanks.
Thank you.
Hi, JP from VMware. I think there's kind of an analogy with the networking I/O scheduling world, except that, basically the hardware, the NIC has some hardware queues, and you might do some reordering and at this point it doesn't matter so much because it goes so fast and you average out quickly. In your case, you have much more,
Right.
Your read is much longer, so I can understand that. Now, I think the question is, when you have like multiple, tenants, clients, that wants to read their block, do you see in storage the same issues that the NIC peak talk was presenting earlier, where you don't have enough, beans or hardware queues, whatever, inside the HG controller to make sure that, you give a class of service for each to much more client.
I think that there is some similarity, and especially in the sense if we talk about the multi-level priorities in the hard drive.
Right.
And yes, I do. It's unclear. So all these protocols that I was talking about, IccNCQ, they're kind of defined in the standards, but there is a lot of open interpretation how they're going to get implemented.
Right.
And we only have a basically custom firmware implementation that we are able to convince the firmware developers to do it, right? But there is a lot of area to explore there, and actually what is the best way to go? How many queues do we want to have, and how many priorities do we want to have at the end? In these type of environments. Right?
Okay, and last quick question about the ICC protocol. I'm sorry, I'm not a storage person, but what are the primitives they provide in the protocol? Like, is that wait or just like I'm high priority, low priority? Like, what kind of
So there are three in IccNCQ. There is a normal priority.
Okay.
There is a deadline command, which with each I/O you can specify a deadline, saying, okay, I want this request to be replied within X number of milliseconds. If it doesn't get if the drive cannot process it within that amount of time, it will drop the command immediately. So the drive will not get busy trying to process this command. So no one else will suffer. The drive will know, okay, I cannot process this within 10 milliseconds.
Okay.
And there is the third one which we used in this study, and that is the high priority commands.
Okay, thank you.
You're welcome.
So I noticed you're using 8 SATA drives. So
right.
instead of NCQ, you pass the priority.
Right.
Have you tried using SAS drives where you use the task?
Right. So there is. I did not, and the reason is pure implementation. So it's not, as I said, this is not very well defined in the standards, and it is not clear to me what field of the data structure actually the SAS drive would use to as a priority. Therefore, I don't know how exactly to create the CDB and have the controller actually create. Transfer this CDB that I create to a drive readable format. Mm-hmm. So all this is, I couldn't find the exact specifications, and that's the only reason why we haven't done it. But I believe it can be done, and it is only a matter of implementation, yes. And so far we only operate on SATA.
Okay, excellent, thanks.